Hey guys, how much heat is released when 105 grams of steam at 100 degrees Celsius is cooled to ice at negative 15 degrees Celsius? Well, we've got four processes happening here. We've got the steam turning to water at the boiling point. There's steam at 100 degrees Celsius and there's water at 100 degrees Celsius. And to condense that steam to water, even though the temperature doesn't change, some heat is released. Water at 100 then has to cool to water at the freezing point before it too changes state into ice, and heat is released in this process as well, even though the temperature is not changing. Finally, the ice has to cool from 0 to negative 15. So we need to figure out how much heat is released at every single one of these stages. Luckily, they've given us some data here. It turns out that to cool steam to water at 100 degrees Celsius, it releases 40.67 kilojoules for every mole of water. Check this out. The amount of heat released is the enthalpy of vaporization times the number of moles. The enthalpy of vaporization, it says, is 40,670 joules per mole. Notice I've converted from kilojoules to joules. And I need the number of moles of water. Now, that's 105 grams divided by the molar mass. You can figure out that number on your own and then just use it over and over again. I'm just going to plug it in as 105 over 18. I'm going to plug this into my calculator so I get the number 4670 times 105 divided by 18. I get 2369.78, and that's in joules. So when I'm cooling 105 grams of steam to water, even though the temperature stays at 100 degrees Celsius, I'm losing 237 kilojoules of energy. Okay, then the water has to cool itself. Now there is no state transition here. Instead, we're simply changing the temperature. To find the Q for that process, we use m delta Tc. Except they gave us the heat capacity in joules per mole, so I guess we're using the number of moles instead of mass. My mistake. The number of moles is 105 grams divided by 18 grams per mole, as I said. We're changing the temperature by 100 degrees Celsius. It's going from 100 down to 0. And the molar heat capacity is 75.4 joules per mole degree Celsius. Now notice the units moles cancels out and degrees Celsius cancels out. I'm going to get my answer in joules. According to my calculator here, it is 105 divided by 18 times 100 times 75.4. That process releases 43,935 joules of heat. All right, state transition number 2, from water to ice. For a state transition, the amount of heat released is delta H times N. The freezing or fusion, melting or fusion of water releases 6 kilojoules per mole. So 6,000 joules per mole times the number of moles. That's 105 over 18. I'm sick of writing that. On the calculator, 6010 times 105 over 18. 35019. 35019 joules. Nice. And my final temperature change, ice from 0 down to negative 15 degrees Celsius. The molar heat capacity of ice is 36.4. So Q equals N delta Tc. That's 105 over 18 times the temperature change of 15 degrees Celsius times the molar heat capacity, 36.4 joules per mole degree Celsius. And on the calculator, 105 over 18 times 15 times 36.4. I get 3181. All right, so now we have the number of joules released at each of these processes. So we're going from steam at 100 degrees Celsius down to ice at negative 15 degrees Celsius, and we've treated each state transition and temperature change separately. The total amount of heat released is simply the sum of all these. In this case, 2369.78 plus 43,935 plus 35,019 plus 3181. When I add all of these together, I end up with 319,113 joules, which is 319 kilojoules of heat released. Now, one thing I do want to point out, this is the enthalpy of vaporization. This is actually how much heat is required to boil 1 mole of water, but it's also the amount of heat released when you take that steam at 100 degrees Celsius and cool it down into water at 100 degrees Celsius. It's the same process, it's just reversed. And I've been lazy with my negatives in terms of the heat being released versus absorbed, because in all of these processes the heat is released. Whenever you're doing a question like this, it's always going to be one directional like that, so you can ignore the negatives, crunch some numbers, add them all up, and get the energy change. Bing, bang, boom. Best of luck.